we consider the equation x minus 4 quantity squared equals negative 25. Now, the solution would be x minus 4 would have to be plus or minus the square root of negative 25. Now, we run into a problem there, okay? What's the square root of negative 25? Well, if you play around with it, you end up saying, dang, okay, I want it to be like 5 or negative 5, because 5 squared is 25, but if you square negative 5, you get positive 25. Negative times a negative gives you a positive. If you square 5, of course, you get 25. That ain't nothing you can square to get negative 25. You can't get negative 25 with any real number. There's no real number that can square and end up with a negative. It doesn't matter if it's negative 25, negative 1, negative 572. You can't square something and get a negative, so there is no real valued square root of a negative number. Okay, but as you should know by now, and you've seen it, you might not remember it, you might not pull it out when you need it, but that's, of course, why we're in this course, so we can do these things. Square root of negative 1 is I. It's not a real number, it stands for an imaginary number. It stands for the basic imaginary number, the square root of negative 1. Okay, what can we do with that? Well, if the square root of negative 1 is I, then the square root of negative 25 can be written first as the square root of negative 1 times the square root of 25, and then square root of 25 is 5, and the square root of negative 1 is I, and then we usually write it with the number before the I, 5I, and of course this multiplication we declare to be commutative. Okay? Now we have to declare it because for real numbers multiplication is commutative, but we just invented imaginary numbers, and we have to decide, do we want this multiplication to be commutative? Well, we kind of do because, we want to be able to reverse this and still have the same thing, many other reasons, and it works out beautifully. Once you invent imaginary numbers, you get complex numbers, like the ones we're going to see here in the next step, just a real number plus an imaginary number. And then you develop the theory of functions of complex variables, which is something most people taking pre-calculus in an on-campus college course are probably never going to do because they're probably not in a curriculum that's going to lead to really heavy-duty mathematics. Although, if you're in engineering, or if you're going to go into engineering, this becomes very important, okay? It becomes very important in the second year of the calculus sequence in differential equations. Okay, well, anyhow. And some pre-calculus students do end up going into engineering, so this is not something that's totally irrelevant to everybody. In any case, we use it with quadratic equations, as we're going to see how they arise in quadratic equations. Again, you're probably already aware of that. Okay, so our equation becomes x minus 4 then is plus or minus the square root of negative 25, and that becomes x minus 4 equals plus or minus 5i, since the square root of negative 25 is 5i. And this equation here represents x minus 4 equals plus the square root of negative 25, or equals plus the square root of 5i, and this corresponds to x minus 4 equals negative the square root of 25. Again, square root of 25 being 5i. Okay, so solution is x equals 4 plus 5i, or x equals 4 minus 5i. Okay, well, let's see what happens if we solve this equation by first expanding the x minus 4 squared to get x squared minus 8x plus 16 using the distributive law. So we get this equals negative 25. And adding 25 to both sides, we get x squared minus 8x plus 41 equals 0. This has solutions given by the quadratic formula. This is of the form ax squared plus bx plus c equals 0 for a equals 1, the coefficient of x squared, b equals negative 8, c equals 41. Well, we plug these numbers in, And we get this, I don't have to read it to you. You can see that every one of these numbers is in place of the corresponding symbol, and then we evaluate it. Now, I haven't gone through every detail, but it's a fairly easy step from here to here. Okay, division being just multiplication by reciprocal distributes over addition or subtraction, which means that dividing by 2 times 1, which is of course 2, distributes over the negative 8 and over this square root. So negative of negative 8 is 8 divided by 2 gives you 4. So you're going to get 4 from this term divided by the denominator. This term simplifies, well, under the parentheses, you simplify, you get 64 here, and you get negative 164 here. And that square root is over 2. Whether it's plus or minus, the square root is divided by 2. Okay, so we have 4 then, plus or minus the square root of negative 100 divided by 2. And of course, the square root of negative 100 is the square root of negative 1 times the square root of 100. So we have this, same as this, except we've messed with that square root of negative 100. And then we can see that since the square root of 100 is 10 and the square root of negative 1 is I, we end up with negative 4 plus or minus I times 10 divided by 2. Well, 10 divided by 2 is 5, and we still have our I. So we end up with 4 plus or minus 5I, which of course is the same thing we have here. Okay? So I probably should have written this out. We could solve this for x by adding 4 to both sides. Since the square root of negative 25 is 5i, what we get then is x equals 4 plus or minus 5i, and that agrees with this. We get solutions 4 plus 5i, which we got here, and 4 minus 5i, which we got here. Now, what does all this mean in terms of the graph of a function? Because some people wanted to start this problem by graphing the function. Now, this was just stated as an algebra problem, but it's connected to the graph. So start